Let's see if we can describe some of these terms. On this circle, line QP has to go through point Q, continue on through point P, and that's my line QP. I noticed that it only hit the circle at one point, so that would make this a tangent line. A secant line would have to hit the circle twice. So if I look at line SP, again, pay very close attention to your markings. This is line SP, hits the circle once, continues on, hits the circle twice through point P. This would be a secant line. Now on the next one, I'm looking for segment OQ, so it has to go from point O to point Q. Since O is the center of the circle, I'm going from the center of the circle to a point on the circle. That's the definition of a radius. Whereas segment SQ starts at point S, goes to point Q, so that's a chord, but it's a very special chord. It went through the center of the circle O, so this would be a diameter. Whereas when I look at the next one, which says chord SR, that starts at point S, goes to point R, but it's just two random points on the circle, so this is nothing more than a simple chord. And then if I look at point Q is the point on the circle that the tangent line QP hit, so that would make it the point of tangency. And these are the terms that I need you to take from today. A couple more simple terms we have. We have the interior of a circle and the exterior of a circle. Not very complicated. If you draw a circle, interior paint is used on the interior of a house or the inside of a house, and exterior paint is used on the outside of the house. So the interior always refers to inside the circle, exterior refers always to the outside of the circle. That will become important as we use some theorems with that terminology. Lines don't have to just be tangent. Circles can also be tangent to each other. So just understand that tangent, anytime it's used with circles, means only hits one exact point on the circle, which is very hard to draw. So coplanar circles that intersect at one point would be considered tangent circles versus concentric circles, which means they all have the same center. So I'm starting all of these circles at this point right in the center, and then I have a very small radius for that small circle, a larger radius for the second circle, and then an even larger radius for that third circle. So when you think concentric circles, think bullseye or archery target or a shooting target of some kind. Those are concentric circles that all use the same center. So let's get into some theorems. This is probably the most useful theorem of circles you will need. If a line is tangent to a circle, then it's perpendicular to the radius drawn to the point of tangency. We know all these terms. So if KM is tangent to circle O in this picture, we know that OL goes from the center to a point, so that's a radius. KM is tangent, so it's only hitting this one point, L, the point of tangency. So whenever I see a radius drawn to a tangent, I know right away that this is a 90-degree angle. This is very important because later on, whenever you can mark those 90-degree angles, you'll be able to say, oh, well, if I connected that, I've got a right triangle, and now I can figure out lengths and measurements inside that picture. Very important theorem. If you only learn one, make sure it's this one. So let's see if we can use this. So KM is tangent to circle O. So right away I notice that radius OL has to be perpendicular to that because of this last theorem. If OL is 6 and LM is 8, we've learned these numbers. This is a 6, 8, 10 Pythagorean triple, so from point O to point M out here has to be a measurement of 10. That would be impossible if I didn't realize that the radius is always perpendicular to that tangent. So this can be simple like the last example, or it can get a little bit more complicated algebra-wise, but the theorem never changes. Km again is tangent to this circle. So OL is a radius, so this is a 90-degree angle, perpendicular. If LO is 5 and LM is 12, I want to know what is NM. Well, at first glance, you're probably thinking 13, which is good, but NM only goes from this point on the circle to the outside of the circle here. I'm looking for that segment. If you saw the 5, 12, 13, that's awesome, but that's all the way from O to M. So we've got to figure out what is just the segment of x. Well, here comes that very first theorem I gave you. All the radii of a circle are the same. So just because OL is 5, we also know that ON is 5. And if we know that O to M is 13, we're simply going to say 13 minus that 5 leaves me 8 left over for that outside piece, NM. This would be the converse of that last theorem, which is used more in proofs than it is to solve things. What it tells you is, if you already know that the radius is perpendicular to a line, so I'm not putting in the 90 degrees, that's given to me, it says that that's also a tangent line, or tangent to the circle. So the converse of that theorem is also true. So here we have OL is 9, LM is 12, and OM is 15. We learned in a previous chapter how to decide what type of triangle that is. If we plug those numbers into the Pythagorean theorem, 9 squared plus 12 squared equals 15 squared, we're going to get 81 plus 144 equals 225. And 81 plus 144 is 225. And we know that if the three numbers work in the Pythagorean theorem, this is a right triangle. And if that's a right triangle, angle L is the 90 degrees, and if that's perpendicular to KM, then yes, this is a tangent, because if a radius is perpendicular to a line, that line has to be a tangent line. Here's another theorem that we're going to be using. If two segments from the same exterior point are tangent to a circle, then they are congruent. You have to understand exterior. Point B is the exterior point, and I have two tangent lines, one hitting A and one hitting C, coming from that same point. So the two segments from that exterior point are congruent. So in this picture, we know that AB is congruent to CB because they came from the same exterior point. Very simple theorem to use. If we look at the next diagram, we have that PX and PY are tangents, and it says that PX is 12. So very simply, since I see that PY is coming from the same exterior point, PX is congruent to PY based on that theorem, so PY is also 12. Very simple.